David Eash from the USGS is going to be talking about long-term and recent-term trend analysis results in floods, high flows, and low flows in Iowa. So, David?
Thank you, Tom. Can everyone hear me? All right. Well, as Tom mentioned, I'm going to be talking about long-term and recent-term trend analysis results for floods, high flows, and low flows in Iowa. And these trend analysis results are coming from a recent study that we completed. This is a streamflow statistics study. And in this study, we computed streamflow statistics for all Iowa continuous record stream gauges for both the entire period of record and for the 1984 to 2013, a 30-year period of record. The statistical analysis include annual probabilities for instantaneous peak flow, high flow for 1, 3, 7, 15, and 30-day consecutive periods, for low flows for 1, 3, 7, 14, 30, 60, 90, 120, and 183-day consecutive periods, and for seasonal low flows, and for 23 flow duration statistics that include the 1% to 99% exceedance probabilities. And this shows the cover of the report. This report was published in January. It's an online report. And you can access this report by searching on the term OFR 2015-2014. There we go. And our cooperators on this study were the Iowa Department of Transportation, the Iowa Highway Research Board, the U.S. Army Corps of Engineers, and the USGS. This report is an update of two previously published reports that presented statistical summaries for selected Iowa streamflow data through 1988 and 1996. And I'd like to acknowledge student help on computing these trend analysis: Patrick O'Shea, Adrian Simonson, Kevin Nguyen, and Nicholas Montgomery. Stationarity is one of the key assumptions of streamflow probability analysis. Stationary is the idea that flood or high flow or low flow generating mechanisms fluctuates within an unchanging envelope of variability. Stationary assumes that future streamflow probabilities can be estimated on the basis of past streamflow probabilities. And a good paper was written by Milley and others in 2008 titled "Stationarity is Dead: Wither Water Management." And in this study, we included trend analysis that hadn't been included in the previous two studies. And we used the Kendalls Tile hypothesis test to test for trends for both the entire period of record, which we call the long-term analysis, and for the 1984, this 30-year period of record, which we call the recent term analysis, for 184 continuous record stream gauges in Iowa. And for this presentation, we'll present the trend analysis results for 55 stream gauges that have at least 50 years of continuous record from 1964 to 2013. Kendall's Tile trend analysis computes a monotonic relation between discharges and time. We use the water years for the peak flow, high flow, and flow duration trend analysis, and we use climatic years for the low flow trend analysis. This is a non-parametric test that indicates the likelihood of a positive or negative trend with time. Kendall's Tile test compares the rank of each annual discharge value with the ranks of the values following it in the series. The second value is consistently greater than the first. The Kendall coefficient is positive. The second value is consistently lower. The Kendall coefficient is negative. The Kendall coefficient value is a measure of the correlation between the time series and time. A Ken p-value threshold of 5% alpha equals 0.05 was used for the Kendall's Tile test, and the Ken p-value is less than or equal to 5% indicates statistically significant trends, positive or negative. Positive trends are increasing trends, the negative trends are decreasing trends. Results may be sensitive to multi-year sequences of larger or smaller values at either end of the record. The Kendall Tile trend tests were performed using the USGS SWStat and PeakFQ programs. This map shows the location of the 55 stream gauges we'll be presenting the trend analysis results for. All of these stream gauges had complete records from at least 1964 to 2013, so at least 50 years of complete records. Drainage area sizes range from 25.3 square miles for Rapid Creek near Iowa City here to 85,600 square miles to the Mississippi River at Clinton here. All these stream gauges are unregulated stream gauges. There is some minor regulation on the Mississippi River, but we did not consider that to be significant enough, so we included the Clinton stream gauge in this data set. Median drainage size is about 3,000 square miles, and mean drainage size and the median drainage size is about 850 square miles for these 55 stream gauges. This graph shows the record lengths of the stream gauges. Mean record length was 74 years, median 73 years. And you can see that we had 8 stream gauges with record lengths from 50 to 59 years long, 14 from 60 to 69 years long, and so on. We had 2 stream gauges with record lengths of over 100 years. And this chart gives you an idea of the magnitude of the stream flow statistics that we computed the trend analysis for, and I'm using the Cedar River at Cedar Rapids as an example. So on the left-hand column we have high flows. We start with the peak flow all the way down through the high flow probabilities, and these are all probability analysis, and I'm using the 2% probability or the 50-year recurrence interval, and the assumption of a stationarity is an important assumption for probability analysis. Then we're down into the flow duration statistics from 1% to 25%. And then we have the low flows. This is median flow, 50% down to 99%. And then we have the low flow, and these are probabilities here, 90-day down to 1 day. So we're using an annual time series to compute the trend analysis, but those annual time series are used to compute these statistics. So you can see that quite a range in magnitude of discharge, 81,700 for the peak flow, down to 205 cubic feet per second for the 1 day low flow. And these red arrows will be shown in the next few slides, and this indicates kind of the flooding range of the statistics. The National Weather Service action stage for flooding at the Cedar Rapids stream gauge is 24,600 cubic feet per second, and this falls between the 1% and 2% exceedances. So this chart shows the trend analysis results for high flows for the period of record for all 55 stream gauges. And so here's the high flow statistics. This is the number of stream gauges with significant trends, p-values less than or equal to 0.05. This is the percentage of the stream gauges of the 55 with significant trends, positive trends and negative trends. You see, if we look at the peak flow statistics, we had 10 of the 55 stream gauges, or 18% with trends. 8 of those trends were positive, and 2 of those trends were negative. So again, these are the results for the period of record, and you can see that we have very few negative trends. These are mostly all positive trends. You can see that the percentage of stream gauge with trends increases as you get to the lower high flow statistics, and by the time you get down to 10%, you've got 80% of the stream gauges with significant trends. And then this shows for the period of record trend analysis results, 55 stream gauges for the low flows. You can see we're not seeing any negative trends. These are all positive trends. You can see the percentage of stream gauges with a significant trend range from 80 to 100%. They have a couple of statistics here where all significant trends for all 55 stream gauges. This is again for the period of record analysis. So these are the trend analysis results for high flow for the recent term, the 1984 to 2013 period of record for all 55 stream gauges. You see we're not seeing hardly any trends at all. There is one stream gauge with a positive trend for the peak flows. And we'll just look at that 30-year period. And again, these are the low flow trend analysis results for the recent term period of record. And again, we're hardly seeing any trends at all. There's a couple of stream gauges at this 99% exceedance and positive trends. There's one stream gauge, 60-day low flow, that had a negative trend. Not really seeing any trends at all when we just look at the last 30 years, the recent term record. This chart is trend analysis results for high flows based on years of record. And this is for 53 stream gauges. We're not including those 2 stream gauges that had records greater than 100 years. So you can see we had 8 stream gauges with records from 50 to 59 years. These records began between 1955 and 1963. 14 stream gauges, 60 to 69 years of record. These records began between 1946 and 54 and so on. You can see we're seeing a difference in the percentage of stream gauges with significant trends by record length. 1903 was a big flood year in Iowa. 1918 was also a big flood year. 1947 was probably the biggest flood year in Iowa prior to the 1993 flood. So there's some differences in the percentage of stream gauges with significant trends based on record length. And this graph then shows percent of stream gauges out of the total of 55 with statistically significant positive trends. On the x-axis, we're starting with the low flows. This is a one-day low flow statistic, the median flow, and up to the high flows, the peak flows. You can see for the low flows, once you up to about the 10%, it's 80 to 100% of the stream gauges are all showing significant trends. We're looking at the entire period of record. And the high flows, we're still seeing trends, but we're just not seeing as many trends, particularly during the flooding statistics. We looked at seasonal low flow trends, and these are 3-month seasonal analysis. So if we look at the fall, this is October to December period that we conducted the trend analysis results on. The tall bars here are for the period of record. These are 1 day, 7, 14, and 30-day consecutive periods for the low flow trend analysis. You can see for the spring season, we're seeing a little bit higher percentage of trends than the other 3 seasons, but for the period of record, we're seeing a high percentage of trends by season. When we look at the recent term period of record, 1984 to 2013, these are the short bars here. We're hardly seeing any trends, seeing a few more trends in the spring than we are in the other seasons. So to summarize the trend analysis results, significant trends are positive. There's few negative trends. For the long-term period of record analysis for the high flows, it indicates significant trends for about 16 to 45% of the stream gauges. And for low flows, indicates significant trends for 80 to 100% of the stream gauges. There's a strong pattern of increasing number of trends going from high flows to low flow statistics. Notable increase around the 5 to 10% exceedance flows. Maybe some trend differences in high flows due to record length. For the recent term, 1984 to 2013 analysis, not really seeing any trends at all, just 2 to 4% for the entire range of stream flow statistics. Possible causes for the period of record stream flow trends. For the high flows, proportion of total precipitation contributed by extreme one-day events has increased significantly during the last century. Although total increases in total annual precipitation are modest, they are concentrated in the high flow statistics. For the low flows, increases in row crop production are related to increases in base flows. Increased base flows could also be caused by improved conservation practices, added artificial drainage, and channel incision. And these possible causes for the low flows come from a couple of papers that were published by Schilling 2005 and Schilling and Libra 2003. Climate is the main cause of increasing stream flow in eastern Iowa and eastern South Dakota. And this comes from a recent USGS report that was published last year. You can access this report by searching on SIR 2015-5146. And they noted increased precipitation is the primary cause of rising stream flow in many eastern South Dakota streams. USGS analyzed stream flow and precipitation trends from 1945 to 2013 for 10 South Dakota stream gauges. And the statistics that they focused on were the mean annual stream flow, the 7-day, 10-year low flow, and then the seasonal flow from May to March for the mean stream flows, and for the 7-day low flows. Are the four statistics that they looked at. And they noted that land use changes likely are minor factors in rising stream flow, with the main factors probably being changes in the timing and frequency of large precipitation events and persistently wetter preceding conditions. So next I'll show 3 graphs that we created for each of the 184 stream gauges as part of the stream flow statistics report. And this first graph is the flow duration curve. And then again, I'm using the Cedar River at Cedar Rapids for the example. On the x-axis, we have percentage of time indicated discharge is equal or exceeded, and then discharge on the y-axis. The blue line is the flow duration curve for the period of record. This is 111 years of record, 1903 to 2013. And then the red curve is for the recent term period of record, 1984 to 2013. And so the 1% flow duration, this is a high flow. This is a discharge that exceeded 1% of the time. This is the median flow. And the 99% flow duration, this is the low flow. This is a discharge that exceeded 99% of the time. So you can see how the recent term flow duration curve is sitting higher discharges compared to the period of record flow duration curve, and there's a little bowing in the low flow range. This is the daily mean discharges graph for Cedar Rapids. On the x-axis, we have water year from October 1st to September 30th, and discharge on the y-axis. And again, the blue line, this is for the period of record, 111 years, and the red line is for the recent term, 30 years. So for October 1st, for the period of record, we have 111 daily values, mean discharge, and those are being averaged and then plotted for October 1st. And then same thing for October 2nd. We're averaging 111 values of mean daily discharge and plotting that discharge, and so on throughout the water year. And then likewise, for the 30 years, we've got 30 values of October 1st mean daily discharges. We're averaging those and plotting that, and likewise for the rest of the water year. So you can see, comparing these two lines, for the recent term, mean discharges are sitting higher than the period of record for almost the entire year. You can see that the average for the period of record, that the average highest discharges during the year occurred end of March, 1st of April, and that's probably due to snowmelt combined with rainfall. But now looking at the last 30 years record, the average highest discharges during the year are occurring in June. This is an annual mean discharges graph for Cedar Rapids. Again, we have 111 years of data, so each of these gray lines is an annual mean discharge for that water year. And the highest annual mean discharge is for 1993. The second highest annual mean discharge is for 2008. The blue line, this is the mean of all the annual mean discharges for the period of record. The dashed blue line, this is the median of all the annual discharges for the period of record. And the blue dotted line, this is the harmonic mean for the period of record. And the red solid line, this is the mean for the recent term, 1984-2013 period of record. The red dotted line is the median for the recent term period of record, and the dashed line, and the red dotted line is the harmonic mean for the 1984-2013. So after looking at a number of these graphs, the question became, is there a statistically significant difference between the mean for the recent term and the mean for the period of record. And to try to address this question, we conduct an annual mean discharge test. We use a Wilcoxon rank sum test that's computed for each of the 55 stream gauges. This is a non-parametric test to test whether two independent paired records have the same medians. Annual mean discharges for each stream gauge from the beginning of record to 1980 and from 1984 to 2013 were tested. The first data set ranged from 18 to 78 years of record. The average was 43 years of record. And the second data set all had 30 years of record. And we wanted to have two independent data sets that weren't overlapping, so this is why we broke the record from the beginning to 1980, and then we skipped a few years, then from 1984 to 2013, so that we'd have two independent data sets to test. And the results were 39 of the 55, or 71% of the stream gauges had statistically significant differences between the median of the annual mean discharges prior to 1981 compared to the median of the annual mean discharges measured after 1983. So the majority of these stream gauges did have a significant difference between these two periods of record. To conclude, significant trends in Iowa are positive. There's few negative trends. For the long-term period of record analysis, few stream gauges, 16 to 45%, with trends for high flows, but many stream gauges, 80 to 100%, with trends for low flows. For the recent term, 1984 to 2013 analysis, not really seeing any trends at all, just 2 to 4% for the entire range of stream flow statistics. The assumption of stationarity is a concern to minimize the bias of significant trends. Stream flow statistics other than peak flow can be computed using a common or variable record length without a significant trend. And for our low flow study for Iowa, we're using a variable record length. We're using a trend analysis result to find the longest, most recent term period of record to use for the low flow estimation of the development of low flow regression equations. For peak flow, we had not seen that many trends, and historic information is important to include in peak flow analysis. So we've still been using the entire period of record, but I attended a conference call last Friday with a USGS Office of Surface Water and with folks from several different state water science centers. And we talked about, we've been requested by the Federal Highways Administration to submit a proposal to look at regional and national peak flow trends, to look at the reasons for these trends, to look at extrapolating observer or predicted trends to the future, and to look at determining when and where adjustments to flood frequency analysis are needed. So USGS will be starting to look at trends and this assumption of stationarity with peak flow analysis. So that concludes my presentation. I'd be happy to answer any questions.
Question for David.
Why do you think you've seen less trends recently than over the longer period?
That's a good question. It really wasn't part of this study, you know, to look at the causes for these trends. We were conducting the trend analysis as just another set of statistics to provide for these stream gauges. So I don't have a good answer for that question. That's a good question, you know, of why we're not really seeing any trends this last 30 years of record.
So you were doing trend analysis on the period of record and then for the last 30 years. I was wondering, how did you decide what time frame to use for the more recent trend analysis, and why the 30 years specifically?
30 years is used for mean precipitation. It's been used by some other agencies to look at a more recent term period of record, so that's why we chose a 30-year period of record to use.
You might give me the same answer as the first question, but one of your last slides shows a shift
is that for the daily mean discharges? Yeah. You know, maybe we're having less snow and less runoff in the spring, and you know, our flooding season is really like in June and July. You know, it used to be, you know, floods were in April and May, but now they seem to be more concentrated in June and July. More of our peak flood season now. So I would suspect that's why.
Any other questions? All right, let's join me in thanking you.
All right, thank you.